in the first phase, PHASE phase, in the first phase, we allow the left turn movement 1 and 5, 1 and 5 for the major street. In the second phase, we allow the through movement 2 and 6 on the main street. Then we allow the left turn at the side street and through movement on the side street too. So 1, 5, 2, 6, 3, 7, and 4, 8. So we divide the traffic signal into 4 phases. I think you don't have any problem understand what phase is. But I want to focus that. Remember this sequence. What do I mean by this sequence? So you will always be major left turn, major through, then minor left and minor through. If you are going to design a signal, design a phasing plan, then use left turn major, left turn minor, or like that. So always remember, left turn major, through major, left turn minor, and through minor. And this is a standard 8-phase layout. We have 8 phases. These 2 phases are happening at the same time. So 8 phases. And the whole, if we take a look at 1, 2, 3, 4, this is a repetition. This is called a cycle in traffic signal. Now, let's assume we only have 2 phases for each direction. So we have 2 phases here for that direction and this direction, 4 and 8. 4 and 8. 4 and 8. 4 and 8. 4 and 8 means the through movement of minor street. So at this time, 4 and 8 can move. So the major street cannot move. So this is a red phase, this is a green phase. And this will be a cycle. And the length of each phase will be called a split. It's counted from the beginning of green to the end of yellow. That will be a split. So a cycle length is the length of the repetition, and the split is from each phase start to its end. Now, in traffic engineering, to optimize, to design a traffic signal at an intersection, you first have to design, to calculate the optimal cycle length. So this is cycle length. Or in this figure, the length of these 4 phases or 8 phases can be called the cycle length by seconds. The reason we want to change the cycle length is when you switch phases, you are going to lose some time. Because when you change from red to green, the drivers won't respond immediately. They are going to waste 1 or 2 seconds. So the more phases you have, the more time you are going to lose. That's why you want to control your cycle length. So you have a longer cycle length with a certain number of phases, you are going to lose less seconds. For example, if we lose 8 seconds within a cycle, then with the cycle length increasing, we are going to get more effective green time in an hour. So this directly means when you change the phase more frequently, you are going to lose more time. So these are 3 lines representing the cycle length versus effective green time. And we know that according to this figure, that the longer the cycle to be, the larger effective green time is. But we also want to reduce the cycle length, because when the cycle length is increasing, the average waiting time of drivers will also increase. So this will be a trade-off of the capacity of the intersection versus the average waiting time. Now, quickly, I change to the next topic called actuated controller. For this plane, if these splits are fixed, it's called a fixed time, a pre-timed controller. But if the split length is variable, that will be called an actuated controller. In an actuated controller, for each phase, each split, we can have the minimum green time, and then we can have the maximum green time. And according to the information that this system got from the detectors, we add the extension time to the minimum green time. So the green time will vary according to the traffic status. And that's why we need a so-called traffic detector. So just remember, actuated controller means the green time can vary. Another concept is called signal coordination. So you are already familiar with this time-space diagram, and these bars are representing the signal status. So if a vehicle travels from here, travels northbound, at this time, the red phase just finished and the green phase just started. And then he can travel because he doesn't see any red on his way. And if a driver starts at this time, he can also he can also pass all these 4 intersections without any stopping. And this width is called the bandwidth. By offsetting these traffic signal phases, we will be able to change the width of the bandwidth of these 4 intersections. Do you understand this? So let's say for example, this intersection, the phasing plan is fixed, but we can move it left or right, move left or move right. If we move it to the right a little bit, then this vehicle will encounter a stop here, correct? So these 4 intersection controllers, 4 signal controllers have to be coordinated. That's called signal coordination. We can have different objectives to do the coordination. Okay, this is another concept. Now, all the coordinations, all the actuations are based on the information we got from traffic detectors. Now, what are traffic detectors? So here on this slide, I'm showing you the history of these traffic detectors. The earliest one was invented in 1928. It was a sonic detector. You can detect the sound. So when you are approaching an intersection, you have to press your horn. You have horn. Then you will be given some time to pass. But this is not very environmental friendly. Then they developed this pressure detector, and then it came to our currently prevailing induction loop detector I'm going to introduce. And with the technology advancing, we're having video detectors and other detectors, a lot of them. But this one is the most frequently used one, called induction loop detector. The mechanism of this induction loop detector is very simple. There is a loop buried under earth, beneath the surface of the road, and it's charged with electricity. When the vehicle passes, drives on it, this electromagnetic field will be changed, will be influenced. So the system would detect it. So in another word, the loop will know that there is a car above it. So that's how the vehicle is detected. And since after understanding this loop detector thing, we will be able to understand a new terminology, a new term called occupancy. So in traffic engineering, occupancy means the percentage of time in which a detector is occupied by a vehicle. When a vehicle is above this, we say this detector is occupied. When there's no vehicle above it, we say it's not occupied. Occupancy is defined by the time percentage of time that this loop is occupied. So this is a new term called occupancy. I want you to know. Now I want to tell you how to detect. How can you find out that there is a loop underground? So if you see something like this, this will mean a newly installed induction loop, like this. All right. Now I want to focus on two things. For the through movement, we have no problem. But for the write movement, I want to clarify these things. So the first thing is right turn on red. Right turn on red simply means when there is a red light, red ball, you turn right. Now, in North America, do you think right turn on red is forbidden or permitted?
Permitted.
Permitted. Yes, it's permitted. But is there any exception?
Because in New York City.
Yes, it's good. So have you already driven in New York City? How did you know it?
My friends told me.
Okay, good. So right on red is forbidden in New York City unless a sign permits it. And why do I introduce this? You will know it later. And it's forbidden in New York State when a red arrow is present. So you see a red ball, you can still turn right. But if you see the red arrow, you are not allowed to turn right. How about Europe? In Europe, this whole thing is forbidden, like in New York City. So when you are modeling an intersection here, you have to be aware if you are using the software from Europe or not. That will be different. Most of our introduced tools are from Europe, so be very aware that if this is the same. Another thing is for left turn. In in the field of traffic engineering, left turns can be categorized into two types: permitted and protected. That's easy. Permitted means you are allowed to turn left, but you have to yield to the opposing traffic. In a protected left turn, it means there will not be opposing traffic. You can turn left without yielding to anyone. Protected and permitted. But what I want to emphasize is, do you recognize these signs? So this is the traffic sign you are going to see in Texas. They have 5 lights, 3 balls, and 2 arrows. In protected mode, the green arrow is on. In permitted mode, this green ball is on. So it's easy to comprehend. This is easy to understand. In Dallas, there was another one, vertical. That's the same thing. And if they combine these, if they put this into two columns, they are the same thing. Now my question is like this. So sometimes you see only 4 lenses, 3 arrows, and 1 ball. Sometimes this ball is missing. Sometimes. So in protected mode, you see a left-hand arrow. What if you see a red arrow? My question is, if you see on the left-hand lane, if you see a red arrow here, does that mean protected or permitted or prohibited? Are you allowed to turn left when the green ball on the through movement is on, but the red arrow is present? No, right? But here it said permitted mode in this figure. Why? So actually this means flashing. Only when the left turn arrow is flashing, you are allowed to